section 233, Poisson's equation and Laplace's equation. So we know that the electric field is just the gradient, or negative the gradient actually, of the potential, the electric potential. So what happens when we take the divergence of E, or rather the divergence of this gradient? So the divergence of E, well, we already know that's going to be equal to the charge density over epsilon naught at that point. And this is also going to be equal the divergence of the gradient, of negative the gradient. So pull that minus sign out. So we have minus the divergence of the gradient of V. So we have basically minus the Laplacian of V. So we get the result that the Laplacian of the potential is equal to the charge density in space divided by epsilon naught. And this is known as Poisson's equation. All this says basically is that the potential basically accelerates. So it grows ever steeper where there's charge around. And Laplace's equation is just basically what you get if you take a region of space where there is no charge. This is called Laplace's equation. And all this says is the acceleration of the potential there is 0. So if it was increasing, it continues to increase. If it was decreasing, it continues to decrease. And if it was flat, it continues to be flat. So much for that. We're going to explore this more in chapter 3. The other interesting thing is what happens when you take the curl of E vector. So that's the curl of minus the gradient of V. Well, no surprise there, that's going to be 0. So the curl of any gradient is, of course, 0. So in truth, you know, the fact that the electric field isn't curly gives us the potential in the first place. So this is basically stating what we already have assumed to be true. Anyway, hope that really helps you.